So we're on to the section of frequency analysis now, and there's two examples I'll take us through here. First of all, I'll walk through natural frequency analysis, so that's eigenvalue analysis in a similar way to buckling, but this time we're extracting the eigenvalues to relate to the modes and the mode shapes, so the natural frequencies of the part. We'll look at the post-processing for that, and then I'll take you through a modal frequency response and look how you can excite the system by putting a dynamic excitation and see how the behavior of the system responds. So for both of these examples that we'll set up, I'll actually do that through the floor example I've built and shown you for the content analysis. It's the same approach. And what we're going to do is just go through the setting up of the modal analysis, a bit of discussion about the solver types that are available, what you can look at for outputs, and then I'll just show you them. So it's one of the more straightforward processes in Genesis, so this should be reasonable to do. I guess one of the things just to discuss for those that aren't so experienced or familiar is why we do modal. So there are two reasons. One, we are genuinely interested in the dynamic behavior of our part. So we model it with all the constraints and boundary conditions and see what we want to know about the system, and see where there may be resonance in the system that could cause us design problems if we're going to be in a vibration type environment in reality. The other application is if you just want to make sure your model that you're building is all connected together and behaving as you'd expect. And there's some really important principles here when you do that. So first of all, if you're going to do that, you'll typically do what's called a free modal analysis. So you'll just simply calculate the natural frequencies without bothering to apply any constraints to the system. And so you can see here, this is my floor model. It's just floating around, and the first mode, that is a deformation mode, is actually, in this case, it's 12 Hertz, and it's just the whole part twisting as a natural resonance. What you're allowed to do there is see that it behaves itself, and second, very significantly, is if you're shaking down a model and making sure it's all connected as expected and it's all behaving as expected, is you should expect to see 6 what are called rigid body modes. Now, for some of you this is really obvious, apologies, but you've covered this in the past, but for others this is just a useful tip. So you run the model as a free modal, you should expect to see exactly 6 rigid body modes. If you see more, it will tell you where parts are not connected and you can go and fix them. And if you see less, it means something is wrong somewhere. It could be some problems that Genesis will encounter is if you have a glued contact between two surfaces, but you also have those surfaces equivalent together, so they're sharing the same nodes in the contact. That can cause some numerical errors, and you'll see that when you don't get 6 rigid body modes. So it just allows you to debug your model and understand it. Okay, before I set up the model, which again will be a quick process for modal, it's worth discussing there are these 2 solver types inside. The default is the SMS eigenvalue solver, and this basically is a more modern calculation to solve the eigenvalue solving, the natural frequency solving, and it's significantly faster than Lanczos. In good size large models, it's easily up to 10 times faster, requires a lot less disk space, and so you can really analyze much bigger problems with larger frequency ranges and larger mesh sizes. There's just a couple of limitations with it. It will be a little bit more prone to having solver problems if your model does have numerical unpleasantries to it. So if you have some really distorted elements or some rigid body connections that are badly defined, then it will sometimes struggle to solve and the errors are not so straightforward. So just keeping that in mind is important. The only other thing to be mindful of is the way it works, and for its speed, it requires a value of the upper frequency to be defined or estimated. You don't have to know exactly your range, but you need to give it a sensible value for an upper frequency. It's just the way the mathematics in terms of it searches the frequency space to do that. So that's there as a default, and I would certainly recommend it as the way to use. But equally, you do have the more robust Lanczos solver, where you can just simply choose how many modes you want and leave the output as that. So that's what we can do. So some other, again, these are subtle but important points to note, and maybe explain why they're happening in Genesis, is when it comes to the input data that defines a normal mode solve, inside the input deck will either be an IGAR card or an IGAR-L card. The IGAR card is the normal modes card, as you can see here, and on it you can define the method. That's what this line is showing us here. And you can see you can choose SMS or you can choose LAN for Lanczos, and it will solve accordingly. Now, additionally, there's an IGAR-L card, which, for those of you that know Nastran format, will know that that is the Lanczos IGAR recovery. That's a historical Nastran card, and many of the preprocessors that will generate a Nastran input file will create IGAR-L by default. So what Genesis does is it will, by its default in solving, if it sees an IGAR-L, it will actually use the SMS, not Lanczos, to solve, because it does solve so much more quickly. So that's recommended. If you want to expressly use the Lanczos, you have to use the IGAR card and choose the method equals LAN. So it's a subtle one, but for those people that are familiar with Nastran format, it can sometimes just surprise them that IGAR-L is running SMS. So just keep that in mind as part of your setup. Okay, so I'll just take you through the setup of doing this and show you the results we get. Again, that is a nice fast one in terms of where we're going. Modal, floor, and here we go. So here's our model. In this case, we're just going to define a free modal. So we go to Eigenvalue methods, we choose new, SMS, we'll choose up to 100 Hertz in this case. You don't need to define how many modes are requested, so actually in this case I won't. In my little slide I said I would, but I won't. It's basically the maximum number of modes to recover, so if there's less than 100, there's no problem. It's sometimes useful to do that just in case you're concerned about creating a really large output file and you don't really care about so many modes. So I can do my normal modes output. No SPCs, no contacts, and here. Outputs are the display shape and the strain energies. Again, that's pretty standard from a modal solver point of view. Now, I'm conscious I'm into an hour and a half, so thanks to all of you that are still attending. I can see actually everybody's still here, so hopefully you're either just doing other work and listening in the background, or you're actually finding this of interest. So that's great to see. That's solved. I can now take a little look at my modes. Now, as mentioned, this is a free modal, so what I'm expecting to see are 6 rigid body modes. So here's my part without any constraints, and so you can see here I have 1, 2, 3, 4, 5, and 6. So if I had more than 6, it means something else is going to be flying around at a near zero frequency. And if I have less than 6, something's wrong in the model numerically. And it really is important to investigate that. And so here I've got my first mode. And what you do see in the output list here in the lower section where our contour results are plotted is you can see I've got my mode shapes. These are calling the vectors, so that's the displaced contour. They exist for the first 6, and then you get your displacements for the 7th mode. And I also ask for strain energy. And in this case, you'll notice that strain energy starts actually at what's described as 6007, which is load case 6, mode 7. And what you can see is there are no strain energy results for the first rigid body modes because there are no strains. When something is moving without deforming, it's just moving rigidly in space, there's no strains to plot. So here you can see the strain energies, you can see where the parts are working in the modal analysis. Okay. It's as simple as that.